Yeah. Hi, Gabe.
Hi. Can you hear me if I'm loud?
What?
So, yeah. So hello everyone. So we're very happy to be here for the second part of the talk of Caroline Terry on the structure of NFOP sets in elementary abelian P groups.
Thanks. Thanks everybody for coming to part 2. We will not be doing like full hypergraph regularity again, so it will be less technical. But so things were a little bit rushed at the end of the last talk, so I just want to kind of recap things to make it clear like what we proved and what's open. So first of all, the kind of manifesto coming out of this work is that there's several distinct ternary versions of stability, and you can detect these by analyzing the behavior of irregular triads in 3 graphs. Okay, so I want to emphasize this because I think this is an important thing to come out of the work that's kind of a soft fact. So there's the second thing I want to mention is that there's many open problems. All right, so I'm going to tell you some of them as I kind of recap the work we did. So Julia and I made these 3 definitions for hereditary 3-graph properties, 3 different ways to constrain the error triads. So first you could say there's 0 error, so there's no irregular triads. You could say there's binary error, which means that there's a set gamma of pairs of pieces of the vertex partition so that every irregular triad uses one of the pairs. And then linear error means there's a set gamma of triples from the vertex set constraining all of the error triads. So I'm not going to, okay, so I'm just wanting to give a quick recap of what we did. So problem 1 is to characterize the hereditary properties that admit 0 disk 2-3 error. So as I said in the last talk, we showed that this really collapses to a problem about a different kind of regularity. So in the literature, it's sometimes called weak regularity. And this is related to work of Ackerman, Freer, Patel, and Chernikov-Starchenko. So if you're familiar with their work on stable hypergraphs, that's the type of decomposition that it's going to collapse into. It's a much less complicated notion of regularity. All right, so we prove some partial results and give a partial answer to this problem, but it's actually still open to characterize. And we give a conjecture that I think is the right answer, but it's still open to give a proof. Okay. And now this is just a comment for the people who are like familiar with the literature here, but we do give a characterization of the properties that are homogeneous with respect to this type of weak regularity. And that's related to work of Chernikov and Starchenko and Fox-Pox-Suk on NIP hypergraphs. But it turns out the characterization isn't the same notion of NIP, something slightly weaker. All right, so then that was problem 1. Problem 2 is to characterize the hereditary properties of 3 graphs which admit the binary error. And now this is maybe the part that got a little bit confusing at the end. So problem 2 is open. So we proved several partial results in our paper, so the ones I was telling you are what I think are the most important, which are the results about the 2 examples. So we found these 2 examples. We showed they're distinct. The edge relation in both is NIP, and neither admit binary error for the same reason, in the sense that we gave a general proof that worked for both. So I think to make a little bit more clear, what do we think is happening here is we think there is some other notion, which we'll just say XOP as a placeholder, so that if you have no whatever this is, XOP, then this should characterize the properties that admit binary error. So, all right, and so our results would say that, all right, if this thing exists, then both properties have to have it. So it's some common definition they both have, but we already know from what we've proved that they behave very similarly. So I really think this exists. I just, we haven't proved it yet. Yeah. Yeah, so under every partition of the variables into 2 pieces, it's NIP. Yeah. All right, so our results show that if this property exists, it's also distinct from like pretty much every other notion you might look at. So it's distinct from the order property, the independence property, the higher order independence property, and FOP2, which I'm about to talk about in more detail. And also anything you can kind of define in a binary way, like the way stability is defined in terms of a bipartition of the variables. Anything that's defined in that way like won't be the right thing here. So it has to be something really ternary. So this is probably like one of the most interesting open questions to come out of the work. So, all right, now I want to get to like what's really relevant to today, which is this the question about the linear error and this definition of FOP. So the third problem is to characterize the hereditary graph properties which admit linear disk 2-3 error. And so now I'm going to show you this definition of FOP, so we'll go through it slowly. So this is a definition. Here I've written it for a formula. So I have a tripartition formula, phi of x, y, z. And I say that it has LFOP in a structure M if there exists A1 through AL, B1 through BL, and I'll draw a picture. So this is FOP2. Okay, so let me make sure I got it right. Okay, so you're given the A1 through AL. And you're given B1 through BL. And then for every F from L squared into L, you get a different sequence of C's, C1F through CLF. So you're given an F from L squared into L. And then I get from this a sequence C1F up to CLF. So what I'm trying to draw here is like kind of the adjacency cube for the formula of phi. So the two of the axes are kind of fixed ahead of time, and then you get the third one, it may be different points for every function. And then how do you decide which points are in the formula and which are out? So, oops, did I draw it wrong? I did draw it wrong. All right, this is why I brought a piece of paper. Okay, so apologies. Okay, sorry. So then, okay, so I want to know, like, you give me a BJ and like CKF. I'll go find the coordinate where these cross, and then I'll compute F of JK. So I don't know, so that's some level on the Z-axis. So this is like F of JK. And then I'll put everything below that into the phi formula and everything above it out. So you do this everywhere. What happens is you build yourself, the function is going to kind of build a surface here, and everything below the surface is saying yes to the formula, and everything above the surface is saying no. So that's sort of geometrically what's going on here. Okay, so but you use different C's for different F's with the same fixed coordinates A's and B's. Okay, so it's really a ternary definition because like all three of the variables do something formally different in the definition. All right, so this is a generalization of the order property in the sense that here what I've done is so this is basically like what would the one-dimensional version of this be? So and it turns out to be equivalent to the order property. So a formula theta xy has the L order property if there are A1 through AL, and then for every function from L into L, there are B1 through BLF, so that theta of AI BJ F holds if and only if I is less than or equal to F of J. Yeah.
Yeah, so you're saying that it's enough to consider F the identity in the bottom of the fact. So is there like a specific function that's enough to check?
I mean, maybe if you like get really clever and you code up something in a larger L, but I think like it's not like this where you can just replace it with say, so like that the hyperplane example was like for F is like J plus K.
And it was in your one of the examples. Right?
One of the
One
examples,
right?
yeah. And so this is definitely like not the same as that. So it's really capturing something different. And so for example, if phi of x, y, z has FOP2, then phi of x, comma, y, z has to have IP. So, okay, so you can never find an NIP example of something with this FOP2. So the point of the comment here is like you could now define like FOP1, FOP2, FOP3 by just changing, where the functions are going. And at the one level, you'll get the order property, and at a higher level, you'll get something else. Okay, so there's a lot of different ways to there's a lot of equivalent definitions of the order property. And then when you go into higher arities, they kind of bifurcate into different things. Yeah, so if I say, this is just saying, I guess like if I write nothing, then I mean for all L. Yeah. So basically like, but you can, in this case, in the first bullet, if it has LFOP2, then it has LIP. Okay. And then on the other hand, there are formulas that have LFOP2 for all L, but only BC2 dimension 1.
And by the way, this makes sense for L equals omega.
Sure. Yeah. Okay. So, right. So the point of this comment at the end is sort of that this is just to help us get a bearings on where this lives. I think it's, as far as I know, a new definition. All right, so this is the FOP, and then one of our main theorems from the hypergraph paper is that a hereditary 3-graph property admits the linear disk 2-3 error, basically if and only if it doesn't have this FOP2. So formally, this happens if and only if there is an L, so that the edge relation has no LFOP in every model of the universal theory corresponding to the property. So in other words, for every hypergraph in the property, the edge relation doesn't have LFOP for some fixed L. So there's a uniform bound on the length of one of these FOPs you can build. Okay, so right. So, but that's not really the main topic of the talk today. So I hope that clears up some of the things that were less clear at the end of last talk. But today I really want to talk about the sort of main motivation for the work, which is coming out of arithmetic combinatorics. So we're sort of just changing gears now. Okay, so what's the kind of main example of the type of problem people study in this field? How dense does a set of integers have to be before it's guaranteed to contain an arithmetic progression of length k? The main motivating example problem. So some of the main tools are Fourier analysis and the higher order variance. And another strategy that's used here is that people often prove things about groups of the form fp to the n for p of fixed prime and n a large integer. And they use this as like toy models to study problems about the integers. So people often prove things first in this type of group, and then they kind of import it into the setting of the integers with possibly a lot of extra work. So that's kind of historically or sort of culturally why we're going to look at these groups today. And the reason for this is also that it's easier to study problems in these groups than general abelian groups, for example. And so I'm not going to go into a lot of the motivation and like background on the additive combinatorics today because there's not time, but my co-author Julia is giving a talk in our workshop next week. So her talk's on Tuesday at 11. So if you're interested in that, I would recommend going because she's like a real expert in this area. So she has a really deep understanding of all these tools. So. All right. Okay, so I'm going to start by going over kind of what the first phase of our project did. So I'll call this Tame arithmetic regularity in FP to the n step 1. So the idea is to prove that combinatorial tameness conditions implies good arithmetic structure. And so I can tell you now that this work is out, that this was sort of where the work started with the stable sets and groups was kind of like a a warm-up problem for the results I'll be telling you about today. So we started by looking at stable and NIP subsets and groups. So given a set A and FP to the N, I say that it's K stable if the graph relation given by X plus Y is in the set A is K stable, meaning there's no K order property for that formula. And similarly, I say that it's K NIP if the relation X plus Y has VC dimension less than K. So these would be what I would consider like combinatorial tameness assumptions. So you're asking some graph associated to the set to omit a certain combinatorial configuration. All right, so I'm informally stating our theorems here, but I'll give a formal statement later. So I just want to give you an idea of what the theorem said. So so we proved first, okay, I guess these are in the same paper, but we proved for any K-stable set A and FP to the N, there's a subgroup H of bounded index so that A has density near 0 or 1 on every coset. So I'm sweeping under the rug what is bounded complexity and close and stuff, but this is the idea of the theorem. And then in the same paper, kind of as part of as a stepping stone to prove the stable theorem, we showed that if A is K and IP, then there's a subgroup of bounded index so that almost all the cosets have density near 0 or 1 with respect to A.
So it's near 0 on every coset or near 0 or 1 of
So in the stable case, it means there's a, like, if you look at every single coset, if you look at the density of A on the coset, it's very close to 0 or very close to 1. No.
Now, how do you define the density exactly?
Okay, Ty, I'm going to give a precise statement in a couple of slides.
Okay.
So this slide just contains sort of an account of like subsequent work done by people in combinatorics and by people in model theory, because there was a lot of it. So I think it was just a really interesting problem, and a lot of really interesting results were proved kind of about using this idea of looking at these like stable or NIP subsets and groups. And in particular with Anand and Gabe, we found some really interesting connections to like model theoretic notions. So I don't have time. I'm not going to go through all of these. So. All right. So step 2 of the program is to do like a higher order, higher degree, higher arity version of these results. So again, the real motivation for this is coming out of additive combinatorics and like these Gowers norms and the techniques developed there. But I'm going to let Julia tell you all about that next week. So I'll just tell you that like what we're going to talk about today is proving like quadratic versions of this. So what that's going to entail is replacing the binary relation X plus Y in A with the ternary relation X plus Y plus Z is in A. And then the structure theorems are going to entail something called quadratic and linear structure versus just linear structure. So I haven't explained in what way like the coset structure can be thought of as linear structure, but I'm going to show you that on the next slide. So there's like a way that there's a sort of correspondence between like when you go up in the arity, you'll go up in the degree of the structure required to prove the theorems, the structure theorems. All right, so, okay, so now I'm going to give you some formal definitions. So the first thing I'm going to do is I'm going to give you a formal statement of the stable and NIP regularity lemmas, but we're going to do it in a slightly different language. Okay, so a linear factor in FP to the N is just a set L of K. Okay, it's a set L of linearly independent vectors in the vector space. Okay, so given such a factor, such as a set of vectors, it comes with an associated linear map defined by, okay, so it goes from FP to the N into FP to the K. So K is the number of vectors in the factor, and we're thinking of K is fixed and N is really huge. So FP to the N is my huge group, and I'm mapping it into this really small, much smaller group. And you get the map by, given an X, you output the tuple X dot product R1, X dot product R2 up to X dot product RK.
Between the X dot, it's just the sum of the X R, R1, R.
Yeah, so it's X1 R1 plus X2 R2, blah, blah. well, okay. I mean, it's the dot product in the vector space. So x dot r would be x1 dot times r1 plus x2 times r2. The reason this is a linear map, I guess now it's good we went over this. You know, if you were to like expand what this is saying, you'll get linear, linear polynomials in the coordinates of x. Because it'll be degree 1. If you're thinking of the coordinates in the r's are like constants and x is a variable. So you'll get a sequence of linear polynomials. Okay, so a fiber of the function has the following form. So given a C bar in the target set, fp to the k, L of C bar will denote like the pre-image of that point. So it's the set of x and fp to the n, so that x dot r1 is c1 up to x dot rk is ck. So, all right, this is, okay, I'm not saying anything. This is just, I'm just writing out the pre-image of the point C under this map. And I'm calling it L of C bar. And the L is, the non-curly L is meant to go with the curly L. So, so if the C is 0, then this would be the set of things whose dot product with R1 up to RK is just 0. And that's always going to give you a codimension K subspace of the vector space. Right, so L of 0 is right, a codimension K subspace of fp to the n. And the other fibers of the function are just the cosets of L of 0. So the linear map, if you take the linear map and then you look at all of the fibers, what you're getting is a coset partition of the group fp to the n. Okay, so I'm just like repackaging the group statement using this factor terminology. All right, so we'll refer to the sets L of C bar as atoms of L. So they're the atoms of the factor, and then I'll let at L denote the set of atoms. Okay, so you have a linear factor, it's like a set of constraints, and now it's associated to a coset partition of the group where, and then we'll refer to these cosets as atoms. So we'll refer to the complexity of L as K, the number of constraints, and so the number of atoms is always P to the K, where K is the complexity.
The index is.
The index is P to the K. Yeah, yeah. All right. So does that make sense now? Why there? So this is why when we talk about coset structure, we will call it linear structure. Okay, so now I'm about to just restate the stable and NIP theorems. So I'm going to give you a little bit of general terminology. So suppose G is a finite group and A is a subset of G and P is a partition of G. So the example to keep in mind is like a coset partition. So then I'll say the partition is epsilon atomic for A if for every part in the partition, the density of A on that part is within epsilon of 0 or 1. All right. And now this is what I mean by the density of A on a piece. It's the, it's the size of the intersection of A with the piece divided by the size of the piece. Okay, and you'll see later why I'm giving this to you as a general definition. Then I'll say that P is almost epsilon atomic if almost every element of the group is in a part of the partition which has this close to 0, 1 density. Right, so we're setting up definitions that then we can use for other types of partitions that aren't just coset partitions. So that's why we've done this slightly general definition. So then I'll say that a linear factor is epsilon atomic for a set A if the partition given by its atoms is epsilon atomic for A. And similarly, almost epsilon atomic if the atom partition is. So again, so this means a linear factor is almost epsilon atomic for A if A has density close to 0 or 1 on each one of the cosets generated by the linear factor. Okay, so now we can give like a succinct statement of our theorem. So this says, I'll read the stable version. So for any epsilon and k and prime p, there is a bound M so that for all sufficiently large n and any k-stable subset of fp to the n, there's a linear factor L of complexity at most M, which is epsilon atomic for A. And then, just replace stable with NIP and epsilon atomic with almost epsilon atomic to get the NIP statement. So I guess the important thing to remember here is the complexity is what bounds the index of the subgroup. So the index of the subgroup is at most P to the complexity. So
Any five index subgroup is a controlling effect.
yeah. You could take the generating set of the orthogonal complement of the subgroup. So linear factors are really interchangeable with subgroup partitions. Partitions obtained by taking a subgroup and looking at all the cosets. Everything's finite index because I guess everything's a finite group here. So. All right, so great. Now we're gonna look at quadratic analogs of this. We're going to define something called a quadratic factor, and we'll start with something called a purely quadratic factor. A general quadratic factor I'll define in a second will have both a linear and purely quadratic component. So the purely quadratic factor is a set Q of n by n matrices with entries from FP. Okay, so instead of just vectors, I now have matrices, and I can associate Q to a quadratic function from FP to the n into FP to the Q, where Q is the number of matrices, by sending X to, the first coordinate will be X transpose dot product the M1X up to the last coordinate will be X transpose dot product MQX. So if you like expand this out in terms of the coordinates of X, you'll get a quadratic polynomial. Is that okay?
It's like the identity.
Oh, thanks. Yeah. So right. So this is like, why did I keep showing you these things about the dot products in the talk on Monday? If Q had just like one thing in it, one matrix, and that matrix was the identity matrix, this would be outputting the dot product of X with itself. So if M is if any of these are the identity, this is going to just be dot product. Okay. So okay. Yeah. We'll assume assume they're different.
And you do as a column vector.
Yeah.
As a column vector.
Yeah, whatever you need to do to make the whatever you need to do to make the multiplication work out. Yeah. So right. Okay, so all right, so the fiber, so now we're going to look at this, we're going to kind of do the same thing as we did in the linear case. So we'll look at the fibers of the function. So I'll take a point in the image space, so a tuple b bar, so b1 up to bq from fp to the q, and then I'll let q of b bar denote the preimage of that point under this map. So it's the set of x and fp to the n, so that for each I from 1 to q, x transpose mix is bi. So yeah. So it's this thing so that like, I've got these quadratic polynomials that are all coming out the way I want. So I'll refer to the sets of the form Q of B bar as atoms of curly Q and denote the set of them by at Q. So now we're looking at a partition that's like very different from a coset partition. So it has like a very different type of structure. And then a general quadratic factor will be a pair. So I'll denote a general quadratic factor by like a curly B for, I guess, why do I do this? Bilinear maybe. So it'll be a pair LQ where L is a linear factor and Q is a purely quadratic factor. Okay, so it's allowed to have like a quadratic component and a linear component. So it's like things of degree at most 2. Same, yeah, in the same FP to the n. Yeah. So then the atoms of the general quadratic factor are all of the non-empty sets of the form L intersect Q, where L is one of the linear atoms and Q is one of the quadratic atoms. And then we'll denote the complexity of it by the pair LQ, where L is the complexity of L and Q is the complexity of Q. Right, so atoms here, so an example of this would be like, what if this just had the one identity matrix in it? Then these would be, the non-curly Qs, the atoms of Q, will be the sets that are like, everything is dot product with itself is 0, or everything is dot product with itself is 1, etc. And then if you add a linear part, you might be just intersecting those sets with subspaces or cosets of subspaces. So that's the type of form that the sets are taking. Okay. All right, so now I can state the first theorem. So I'll say that a quadratic factor is almost epsilon atomic for a set A if the atom partition is. So this means that almost every group element is in an atom of the factor whose density with respect to A is near 0 or 1. So A is like taking up almost all or almost nothing of most of the factors involved, or most of the atoms. Most of the pieces look like they're either in A or disjoint from A. Then I'll say that the VC2 dimension of a set A in FP to the n is the VC2 dimension of the relation x plus y plus z is in the set A. So I haven't defined this, but this is like the higher order version of VC dimension that makes sense in 3 graphs. All right, so our first theorem says, so I'll go through it slowly, but informally it says that if you have a set who's got finite VC2 dimension, it looks like a union of quadratic atoms. So formally, for every k and mu and every omega, so you can kind of ignore this omega for now. There's a constant, there's a bound C, so that for any sufficiently large n and any subset A with VC2 dimension less than k, there's a quadratic factor of complexity LQ such that a list of things holds. Okay, so B is going to be a combination of the level sets of those bilinear maps and cosets of subgroups. And so first of all, the first bullet tells me that the complexity is bounded. So L plus Q is at most this constant C. And that's going to bound, for example, the number of atoms in the partition. And then the second thing in the first bullet is that the rank of B has to be high. You don't really need to worry about what this means. It's a technical condition. I'll just tell you orally, it means like this is the minimum rank of any non-trivial linear combination of the matrices in the quadratic part of the factor. You kind of need you need it to be high rank to sort of do things that are interesting. All right, so you can always make it as high rank as you want. That's what this part says. And then the second bullet says B is almost epsilon atomic for A. So almost all the atoms of B are either almost entirely contained in A or almost entirely disjoint from A. Yeah. Yeah, sorry. Yeah. And then the third bullet says that there's a set omega of atoms from the factor whose union has very small symmetric difference with A. I mean, so P to the n is the size of the whole group. And so saying that A symmetric difference with this union is small is saying that, A looks essentially like this union of atoms. And you get the omega by taking the set of atoms where the density of A is close to 1. Does C depend on for B? P is fixed. Yeah. Okay. P is fixed for the whole talk. We're just working in FP to the n for a fixed P.
Caroline, can you, the matrices in the quadratic form, are they symmetric?
Yeah,
Oh, they get to be that part of the theorem, right? Like
that's
you
part of the
put-
definition of a factor.
it was always symmetric matrices? I didn't
Yeah,
miss it. Okay.
yeah. Right, and okay, so okay, okay, so this theorem uses tools in additive and extremal combinatorics. So we use a quadratic version of the arithmetic regularity lemma, where okay, it's a higher order version, and we use a counting lemma for 3 graphs, and then other techniques from additive and extremal combinatorics. All right, and like I said, Julia's going to talk a lot about like why you would expect this theorem to be true based on the tools in additive combinatorics. Yeah, no, so actually this is a good example of a really ternary definition. So it's like in VC dimension, you shatter like a box, like a set. And in VC 2 dimension, you shatter a Cartesian product of sets.
There's two then. Is that
Yeah, I
two-
mean,
two different-
yeah, I don't, so this is so I'm not like gonna guarantee you that I'm using the same indexing as is used in the other papers written by other people, but this is the indexing I use. So it's to remind you that it's a Cartesian, you're shattering Cartesian products of 2 sets. So you can't do it with like a binary relation.
And also, I would like to know that these sets you get by these quadratic things are actually have that property.
They do, they do, they do, they do, they do.
Concept has it.
They,
Yeah.
yeah, they do. Okay. They're, a quadratic atom has VC 2 dimension 1 or 2, I don't remember. It's very low, like a subgroup. But that's a good question, yeah. Okay, so now I want to tell you about the theorem for the FOP2 sets. So I'll say that a subset of FP to the n has the K FOP2 if the ternary relation x plus y plus z in the set has K FOP2. So this is this picture over here where you've got like a z and an x axis, and for every f you can find a y axis to cut out this surface. So if you can't do that, or if you can do that, that's the KFOP2. So that's like this weird order property. All right, so I think kind of the main motivation for all of this work was to prove some analog of the result about stable sets for this kind of setting. So this is what we have here. So what's written here so far, it's identical to the VC2 statement, except I've replaced that A has finite VC2 dimension with A has no K FOP. And then the conclusions up to this point are identical. Okay, and that makes sense because if you don't have KFOP, you also have bounded VC2 dimension. So I'm going to add a conclusion that makes it different. And so this is the additional thing you get if you also insist there's no FOP2. So what you get is that there is a set sigma contained in at L. So this is just the set of purely linear atoms, meaning just the coset partition. So there's a set sigma of the linear atoms whose size is not too large, and such that for every atom from the big factor, the quadratic factor, if the atom is not epsilon atomic with respect to A, so if it's like an error atom where something bad is happening, then the linear part of the atom comes from sigma. So formally speaking, B has the form L intersect Q for some L coming from this set sigma. So it's a little bit weird because I'm not saying like every atom has density 0 or 1 with respect to A, but the ones that fail can be constrained by a small set of purely linear atoms. So the note is, okay, the error atoms. So by error atom, I mean an atom where the density of A isn't really close to 0 or really close to 1. So all the error atoms are contained in a small number of purely linear atoms. So kind of the way of thinking in additive combinatorics is that like the linear structure is somehow lower order than the quadratic structure. So what we're doing is constraining the error using lower order structure. So we have a quadratic decomposition and all the error is controlled by linear structure. So it's kind of analogous to the hypergraph definitions. Okay, so in this case, we say that the factor B is almost epsilon atomic for A with linear error.
What is Q? Normal.
Q is the quadratic part, the pure, so B has two components. It has a purely linear factor and a purely quadratic factor.
And the Q is the bottom.
So it should be, it has the form L intersect Q for some L in sigma and Q in curly Q. Okay, so every atom of B has this form for some L in curly L and some Q from curly Q. Okay, and so this is the special thing here is that you kind of can know where the linear parts are coming from. All right. So and this is really the theorem that like kind of forces you to acknowledge that like you have to kind of shift to looking at controlling error rather than like eliminating it.
And how do you see that this generalizes the stable case, the not binary case? Is this obvious that it does?
Well, I mean, what do you mean in what way?
Because there, I mean, there you actually did eliminate all the errors.
Yeah. So this is what I'm saying is there's lots of different ways to attempt to like generalize these theorems. I mean, it's just a different phenomenon, I guess. So like what we're having here is like tame behavior over the linear structure.
Yes, so it's not the case that under special conditions you recover the stable regularity. That's not the case.
No, this is a fundamentally different problem. Okay, so I don't have time to like, there's a way of phrasing this for like hereditary group properties that makes it clear that like this is like really a different problem. How to get rid of, like if you want to get rid of it entirely, get rid of the error entirely, like you may need to assume stable or something. That's open. So it's open. What would get rid of all of it entirely? Do you know that if it's stable, you don't have any error, but then you can't have any non-trivial quadratic structure.
Stable means for any partition.
No, for the binary graph. Binary graph. So it's there's a complicated story there. Okay, so I don't have time to totally like flesh that all out. Okay, but things behave in kind of weird, non-intuitive ways based on like your model theoretic intuition possibly might tell you. As like I can't speak for everybody here, but okay, so because like okay, I was not like looking to prove this theorem. I don't like, at first I did not like this theorem, but you cannot get rid of these linear error atoms. And the way that we came up with the proof was like making a geometric kind of analog to a version of the proof for the stable sets. So there's a way in which this is like kind of the proof can be seen as like a geometric analog of the stable proof. Okay, but you cannot get rid of the linear error in that proof. So, all right. That's not the proof that ended up in the paper because we found a shorter proof. So, and the proof in the paper uses stable regularity for some graphs in an auxiliary group. So that's another way in which like you use stability, but in a different place, like in a different quotient structure to prove this theorem. So the rank is that it's the minimum rank of any non-trivial linear combinations of the matrices used to define the quadratic factor. So I didn't define it. Okay, but it's about the rank of the matrices involved in the definition. Yeah.
So when you define the linear factor, you just assumed outright they were linear independent because it's
Yeah.
kind of like the analog of that or something.
Yeah, so in order to know all the atoms have about the same size, you need to assume the rank is large, for example. So
Isn't the rank bounded by n?
yeah. But L and Q are fixed and N can be, N is huge and L and Q are bounded.
But omega can always give you a number.
Yeah, I mean,
bigger
so
than
you
N.
may need to pick bigger and bigger N if you pick a different omega.
Oh, okay, so N, we can.
Yeah, so the quantifiers
N
all,
can-
yeah, the
N
quantifiers are for all K, epsilon, omega, there's a D. So that for sufficiently large N. Okay, so, right, so with the, so this is like the main structure, this is like the main structure theorem we proved. And it uses the VC2 result as well. So I want to end by kind of relating this back to the hypergraphs. So okay, so we're going to translate this back into the hypergraph decompositions applied to the sum graph, like the 3 uniform hypergraph you get by looking at the sum graph. So given a set A and FP to the n, we'll let H sub A denote the 3 uniform hypergraph with vertex set FP to the n and edge set the triples XYZ who sum into the set A. So from a set, I can define this hypergraph, and now I'll think of it as a hypergraph. All right, so don't worry, I'm not going to go back over the definition of a TL decomposition, but I'll just remind you that a TL decomposition for a hypergraph is like a partition of the vertex set along with like a partition of the pairs. So I'll say that such a partition of FP to the n is quadratically structured if it basically comes from one of these quadratic factors. So formally, this means there's a quadratic factor B, so that the vertex partition is exactly the atoms of B. So the atoms of B partition the vertex set because the vertex set is FP to the n. And then the edge colors are obtained by taking 2 atoms from the factor and then intersecting B1 cross B2 with something I'll define in a second. So beta of C bar. Beta of C bar is the set of pairs whose dot product, so that X M1Y is C1, X up to X MQ, Y is CQ. So so if you give me a pair XY, I can definitely compute what are these, what are so each of these is a symmetric bilinear form basically, and you're just partitioning the pairs according to the value that they give you. So if there was only one matrix and it was the identity matrix, this would be exactly the decompositions in all the examples from Monday. Because you would be partitioning, the atoms would be the kind of level sets of what you get by dot producting things with themselves. And the edge colors would be obtained by computing like X dot Y and then partitioning according to that outcome. All right, so this is a way in which these vertex decompositions come up naturally out of the quadratic factors. All right, so, and one of the reasons, another place the rank comes into play is that if the rank is very large, then this decomposition will always have the equitability conditions that we wanted it to have. So that would mean the atoms will all have about the same size. So you'll get something close to an equipartition of the vertex set. And the elements in key edge will be highly regular. They'll be epsilon2 regular for some really tiny epsilon2. So the rank's important for guaranteeing that you're getting the type of decomposition you want for the type of hypergraph regularity we were talking about on Monday. All right, so an element of, one of the triads. So if you remember, maybe you don't, there was a lot of definitions. So a triad from the decomposition would be like a 3-partite graph obtained by picking 3 pieces from the vertex partition to be the vertex set, and then picking between each pair of those like an edge color. So the only thing I want to point out here is that a triad here will be a 3-partite graph whose vertex set is the union of 3 distinct atoms from the factor. So that will mean like an L1, so and everything, an atom in the factor looks like an L intersect Q, where L is a linear part and Q is a quadratic part. So it was just a preview. All right, so the point is, the thing I want to point out, right, is that if I take one of these, there's going to be 3 linear atoms involved and 3 quadratic atoms involved. All right, so one thing you can prove, one thing we proved is that given any set A, you can obtain like regular hypergraph decompositions so that the decomposition P is quadratically structured. So for any set, for any epsilon1 and function epsilon2 and any sufficiently large n, any A and FP to the n has a quadratically structured regular decomposition for its ternary sum graph. So the results on Monday would say that like such a decomposition exists without any assumptions on the structure, because you would just apply the regularity lemma to H sub A. And so the additional condition we're getting here is that you're getting a hypergraph decomposition that's regular and where all of the pieces are being defined out of this quadratic factor. So everything's defined using these cosets and like level sets of bilinear forms. All right, so this is analogous to like a result in a paper by Green, where he uses the linear arithmetic regularity lemma to show that you can always give a partition for the sum graph where it's a regular partition and where the pieces are cosets of a subgroup. If you're familiar with that, it's like a higher order version. All right, so we're moving through these results. The point is I want to really explain why we called it linear error in the hypergraph case. So, all right. You can also translate the VC2 result into a result about hypergraphs. And here what you get is that you get a decomposition that's quadratically structured. So the pieces are all coming out of these bilinear forms and cosets, and where all of the regular triads have density close to 0 or close to 1. So, all right, so now we're back to the FOP2 case. So what this tells us is that if you have a set A, which has no FOP2, then you can get a quadratically structured regular decomposition for its ternary sum graph, which has linear error in the hypergraph sense. So what that means is that there's a small number of triples from the vertex partition where all of the irregular triads live.
What is the difference between this and the VC2 case? Can you?
There's the linear error is the difference.
There was. Can you go back just to previous slide to show the difference? But there was this epsilon1 homogeneous.
Yeah. So you get this as well in the FOP2 case because it's So it could also say epsilon1 homogeneous here. Okay, so I want to show you how do you get the linear error in the hypergraph case. So what that means is like we want to get a set gamma of triples of pieces of the vertex partition that contain all the irregular triads. Okay, so that's so gamma is going to be like the hypergraph linear error we're looking for. So the way we do it is we apply our structure theorem for the set A to get a quadratic factor and a small set of linear atoms from the factor so that all of the non-atomic atoms have linear part coming from sigma. So you do this first, and then I can just define gamma to be the set of all the triads whose vertex set has this form. So it'll have it'll be 3 atoms. So there's 3 linear components, one for each piece in the, each of the pieces. And I'll put it in gamma if the linear pieces sum into sigma. So, okay. And so the reason that this so the point is that you get a small number of, the gamma will not be large because the sigma is not large. And so you exactly get the form of this error set in the hypergraph is exactly what you get in the definition of like linear error for a hypergraph. So, okay, I guess, all right, there's also, go ahead.
I have a question. So this theorem follows from the theorem that you showed us a couple of slides ago about the K of the FOP, the KFOP2 thing.
Mm-hmm.
That's the question, whether it follows from that or it follows from the other paper or the other.
So No, it's all in the arithmetic paper. So we have to build up some machinery to be able to translate between the structure theorem about the set into the hypergraph thing. But once you do that, then it follows from that. So you do have to do some work to show that you can go from this, a structure theorem for the set. So like the B, then you need to do a little bit of work to show that like the corresponding P is a hypergraph decomposition with the right properties. Does that answer your question?
Yeah. So you're not using the other paper to prove this. So
No,
right, yeah,
no.
I understand. Okay.
The proofs though, I mean, were developed together because they're
Yes.
somewhat, yeah.
Mhm.
Okay,
What
so
if
I
you
guess
just try? I guess if you just try like naively to apply the previous paper to this, you'll just get something horrible and you won't get anything, any meaningful thing.
right, there will be no structure to the vertex partition, for
Yes.
example.
Okay.
All right, so I'll stop there. Thanks for listening.
Thank you very much. Are there any questions?
Can you imagine something for higher than 3?
Yeah, so I mean, what's happening is there's these Gowers norms, and they kind of have a loose correspondence to different types of arithmetic structure at every level. So that's like for the U2 norm, there's kind of a correspondence with linear structure. For the U3 norm, there's a correspondence with the quadratic structure. And so the people in additive combinatorics understand kind of what happens as you go up. Okay, you get a cubic polynomial, you get cubic structure at the next level, et cetera. So yeah, so obviously, so you can ask these questions like going all the way up. Yeah.
And you don't expect this proof to just generalize, or you do?
Yeah, maybe. Yeah, I don't know. I mean, maybe you could do it. I haven't done it.
But in
I don't
the
know.
abstract case, not in the arithmetic case, you actually did do it for every n, right? Or no, not only for
No,
any.
so
I
this
don't know.
is like this is at level like we're only looking at quadratic structure. So what you would do at the next level is look at like the 4-ary sum graph, and you would get a different type of structure coming from.
Oh, okay,
Yeah.
right.
Yeah, okay, sorry, can I take this up? Should do? Okay, yeah, so in the, when you take this FPN to the end or something, and you get this quadratic kind of structure objects around, are those things definable from A? You add the predicate A, right? So I mean, you know what I mean? So it's like a little, so with the FP, yeah, just is it something, because it's not, these are not defined in the vector space structure, because you've got this squares, right? But is it something you can get from A?
I don't know, because there's no theory around this like there was with the G0.
Yeah,
whatever,
okay.
So I don't know.
Okay, thank you.
Yeah, of course. Yeah. No, I mean, the proof will not do that for you. I mean, it's sort of. Okay.
No.
The elements of the structure are the vectors. Then you can't do.
I mean, you're asking a question I don't know the answer to. I think it's like that would be new work or something. Okay.
Are there any other questions? Online, maybe? Let's thank the speaker again.
Thanks.